In this lesson, we're going to be looking at some very unique types of functions known as piecewise functions. Okay, so we're going to look at how we can graph piecewise functions. To do so, it's going to require us to be very strong with the parent functions that we put into our library in our previous section. And then we're also going to be able to write a rule that represents the graph of a piecewise function. Essentially, given the graph, can you write an equation to match it? Right, now a piecewise function is a function defined by more than one equation. Different parts of its domain have separate equations or rules to follow. All right, so here is an example of one type of piecewise function. It has three parts or three rules to it. Okay, the top rule is f of x equals x squared, but you only would use that rule for domain values that are less than or equal to 1. So f of x equals x squared if x is less than or equal to 1. F of x would equal 3 only when x is between 1 and 2. Notice 1 is not included there because we already included it in the interval above. And then the last rule, f of x equals x, will only be used when x is greater than 2. Notice how the rules correspond to the graph over on the right-hand side. This is where your knowledge of your library of functions can really come in handy. F of x equals x squared, we know that that is a square or quadratic function, and graphs to be a parabola, right? So in terms of the graph, we're looking at this piece right here. Okay, choose the crayon. This piece. All right, notice the domain of that piece alone in blue would be any number less than or equal to 1. The middle rule, f of x equals 3, that's a constant function, which we know leads us to a horizontal line, this section right here. Notice that the endpoint on the left does not include 1. The endpoint on the right does include 2. And then the last rule, f of x equals x, that's our identity function right here. Okay. All right, so one thing you should be able to do is evaluate a piecewise function with different values in the domain. Okay, so f of 4 for this particular function. All right, you want to find which rule should be used for the x value of 4. 4 fits into the bottom domain right here of x greater than 2. So we're going to say that f of 4 equals 4 then. Okay. The next value that we'll plug in is 2. F of 2 fits into this domain. Okay. And that will evaluate out to 3. And then lastly, f of negative 2 fits into this domain. So f of negative 2 would mean you need to square the negative 2, which would result in 4 as well. Okay. Now what's the domain of this graph? Well, it would be all three of these put together. And if you think about them all combined, then it actually is going to give you all real numbers. Okay, and the range of a piecewise function can be very unique. You have to graph in order to tell what the range is. So looking at the graph here, you can see there is a low point. It has a y-coordinate of 0. And then there are no high points, right? The blue curve keeps moving upward, so does the green curve. So that means our range would be y is greater than or equal to 0. I do want you to notice that the curve does pass the vertical line test. It even passes it right here, as well as right here. So we are working, remember these are called piecewise functions, right? We are working with functions. So whenever you go to graph one of these yourself, make sure it passes the vertical line test. All right, let's try one ourselves. Okay, you're given a function with 3 rules to it. We need to graph it and then state the domain and the range. Okay, I'm going to graph it in stages with different colors. Okay, so the top rule there is a square or quadratic function, so we know this piece should graph in part to look like a parabola. Okay, and I'm going to make a quick little XY table for this. And the key here is in the domain that is associated with that rule. That tells you what values you're allowed to plug in for x. All right, so I'm going to plug 1 in. 1 squared is 1. Go ahead and plot it. And I'm going to plug 2 in. We know 2 squared is 4. And I'll plug 3 in. 3 squared is 9. Okay, I'm not going to be able to fit any other integers on integer values in for x because they would take me off the graph. Okay. Based on that domain, when I go to connect these points, I'll put an arrow at the top but not on the bottom. Okay. All right, next piece, do in blue. Its domain is any number between -3 and 1. Notice this is a constant function, f of x equals 6. All right, now here's where students sometimes get hung up. The domain does not include the value of -3, right? You still need to plug -3 into the function for that rule, okay? Reason being, you need a place for this piece to stop graphically, okay? So I'm going to say that f of -3 for that rule would equal 6. And understand that that -3 technically was not supposed to be used for that rule. Okay, I just need a place for this piece to stop. So graphically. So when I go to plot this point, I have to plot it as an open circle, as an open point. Okay. Now pick some other values of x that do fit inside that interval. So I could pick -2, right? -2 is between -3 and 1. So f of -2 should be 6. And that can be a solid point. Same thing with -1. F of -1 should be 6 as well. And I think you get the idea. You're going to be able to do this all the way until you get up to x equals 1, which is the other value at the other end of that interval. If you were to try to plug 1 into that piece, you'd get 6 as well. And that should graph to be another open point. Okay, connect all of them to form what looks to be a horizontal line segment. Both endpoints are not included. All right, last piece we'll do in red. Notice its domain is less than or equal to -3. And this time the -3 is included. So when I plug that in and get a y value, that point should be plotted as a solid point. Okay, f of x, or I'm sorry, f of -3 on that rule would turn out to be 3. right? You're taking the negative of negative 3. So f of negative 3 equals 3. Go ahead and plot that as a solid point. And now the other values that you choose for x, they have to be smaller than negative 3. So I'm going to choose negative 4 next. It'll give me 4. And negative 5 will give me 5. And I think that's enough to see the pattern. You have a linear function. Only points to the left, though, based on that domain. Notice your graph passes the vertical line test, right? It is a function. All right, what is the domain? Well, if you consider all 3 domains together from each rule, they'll combine to give you all real numbers. And then if you look at the graph, you can see that your range would be any value greater than or equal to 1. Okay. All right, next example, we're working in the opposite direction. So this time we are given the graph of the function, and we need to come up with a rule to define the piecewise function. Okay. Now there's technically a couple different ways you could define this based on how you look at the graph. The way I'm viewing this, I see that this piece right here all together represents an absolute value function. You could break it up into 2 linear pieces if you wanted. All right, and then this piece obviously represents a constant function. Okay, so let's come up with our rule here. I'll do it all in blue. So we'll start with, give me an f of x equals, and put your brace in there. And let's start with the absolute value piece. That comes from our absolute value parent function. So I can just say the absolute value of x, f of x equals the absolute value of x, if x is less than 2. Okay, because that green piece has a domain of anything smaller than 2. The purple horizontal piece, being constant, would give me f of x equals 1 if x is greater than or equal to 2.